So we've looked at individual events and we've looked at compound events, the probability of A or B happening. But let's talk about conditional probability. The probability of event B happening given that event A has already happened. All right, so for that, we need to take into consideration the probability that event A and B have happened. What's the probability of event A and B divided by the probability of event A? Now it looks like a crazy formula, and after we look at it, I'm going to kind of show you a simpler way of thinking of it, especially when you're dealing with tables. But sometimes this formula is an easier way. But let's go on. The following table shows displays the 100 senators of the 115th U.S. Congress on January 3rd, 2017, viewed by political party affiliation and gender. And they give us our totals. So make sure you note which columns are totals. What is the probability that a senator is a woman? So females, the probability of being a woman is 21 out of 100. What's the probability of being a Republican? Well, how many Republicans are there? Well, there are a total of 52 Republicans. What's the probability that the senator is a woman or a Republican? So let's remember how we did the ors. So the probability of being a woman was 21 out of 100. So this is probability of woman or Republican. So woman or Republican minus the both. So how many were both? 5. So that would be 21 plus 52 minus 5 gives me 68. And I could have counted on the table too. What's the probability that a senator is a woman and a Republican? Well, that's easy. That's female and Republican. That's 5 out of the 100. But let's say we already knew that the senator was a woman. What's the probability she's a Republican? So the probability that the senators are Republican, given that we know it's a woman. Well, according to the formula, we'd take the probability of it being a woman and a Republican divided by the probability of being a woman. So woman and Republican was 5 out of 100. I'm sorry, I looked at the wrong line. 5 out of 100. Divided by the probability of being a woman, that's 21 out of 100. And so kind of the 100s kind of cancel out. And so it's 5 out of 21. I like to think of it as I'm reducing my sample size and I'm only looking at the column that's women. So I already know it's a woman, not a man. Ignoring this column completely. So the probability of being a Republican knowing that it's a woman, well, there's only 5 Republicans and only 21 women. 5 out of 21. What about the other way around? Given that the senator is a Republican, what's the probability of being a woman? Changing it around. The probability of being a woman, given that they're a Republican. So using the formula, probability of being both, this time divided by the probability of being a Republican. So that would be 5 out of 100 divided by Republicans, so we're 52. So again, we can think of it as, well, there were 5 that were both, and there were 52 Republicans. You're reducing your sample size. That's the way I kind of think of it when I'm looking at the tables. Now, we talked about mutually exclusive. That means there's no way they can happen at the same time. But when we're talking about these types of events where it's conditional, that one thing happens, then the next one happens, they can either be independent or dependent. Independent means that the occurrence of one does not affect the probability of the other. Now, dependent means that they do affect each other. Now, mutually exclusive means that the occurrence of one prevents the other one from happening at all. So let's see the difference there in each of these. The student is a freshman, the student is a sophomore. Yeah, those are mutually exclusive. There's no way they can happen at the same time. The student is on a basketball team. The student is taller than 6 feet tall. Does one affect the other? Well, that's independent. The student is a woman. The student belongs to a sorority. Well, actually, being in a sorority, you have to be a woman. So this one does depend on the other. The student is a woman. The student belongs to a fraternity. Fraternities are for men only, usually. I don't know if that's changed since I've been in school. Those would be mutually exclusive. Student is a woman. The student was born on Sunday. Those are totally independent things. All right. So we know that if they're dependent on each other, if one's affecting the other one, then when the first one happens, it's going to affect the outcome of the other one. So it's going to affect B happening. But if they're independent, it's not going to affect them. So when it's an and situation, and we want this one and this one, we're going to be multiplying our probabilities. So when it was an or, we added. So P or B, A or B, we added. When we want both of them happening, we multiply. So let's do an example. 2 dice are rolled. Let A be the event on the number on the first die is even, and B is that the number on the second die is 6. So does the first die affect the second die? No, these are independent. So what's the probability of A happening? Well, even, there's 3 of them that are even out of 6, so that's 1 out of 2. The probability of the second die being a 6. Well, there's only one way that can happen. The probability of the first die being even and the second die being a 6. That's going to be 1 out of 2 times 1 out of 6. That's 1 out of 12. So, and we multiply. Right? Now the next example deals with cards. And I know some people have dealt with cards a lot in their lives. They played solitaire, they played cards with their family. But I found that some people don't have those experiences with cards. So let's talk about a deck of cards. A deck of cards has 52 cards. And there are 13 cards in each suit. And what we mean by suits is there are hearts, diamonds, spades, and clubs. The hearts and diamonds are red. Ooh, almost ran out of room on my page. And these are black. So half of the cards are red and half of them are black. And there's 13 in each set. And that's made up of an ace, which also sometimes counts as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes Jack, Queen, and a King. And I should have wrote out that this was an ace. So for those who aren't familiar with cards, this is how a deck of cards is laid out. I invite you to go play a game of solitaire so you can see them. So, because these pop up a lot. 2 cards are drawn from a deck with replacement. That means I pull a card and then put it back. So if I do that, then I'm not affecting anything. Each one is going to be independent. What is the probability of drawing a queen and then an ace? So the probability of a queen and an ace. So the first card being a queen, there'd be a queen in each of those sets. So there'd be 4 queens out of the total 52. And how many aces would there be? Well, there'd be 4 aces out of 52. And that would be, and by the way, if you have one of these calculators, if you didn't know you could do this, if you press the alpha and then y equals, you could type these in as a fraction if you are not good with fractions. And not only will it give you your answer, but it gives it to you in fraction form. Now be careful on the homeworks whether it's asking for the answer in fraction or in decimal. Sometimes it does both. 2 cards are drawn from a deck without replacement. That means they keep the card after they draw it. So they will affect each other. So let's think about this. What's the probability of drawing an ace and a jack? So when I go to draw the ace, there's 4 aces and there's 52 cards. When I go to draw the jack, there's 4 jacks, but now there's only 51 cards because 1 card was already taken, So I would do 4 out of 52 times 4 out of 51. That gives me 4 out of 663. 2 cards are drawn without replacing. What is the probability that they're both jacks? Okay, so the first time there's 4 jacks and 52 cards in the deck. Now the next time I go, I've already pulled a jack. So there's 3 jacks left and only 51 cards. Now I'm going to be extra lazy on this. If you didn't know that you could copy and paste on a TI, then you're welcome. You can just go in and edit, and that is going to be 1 out of 221. What is the probability, oh, this is without replacement again, of getting an ace, king, then a queen? Oh goodness, that means we're going to be multiplying 3 things: ace and a king and a queen. So there's 4 aces and 52 cards. When I go to draw, there's going to be 4 kings and 51 cards. Then there's 4 queens and 50 cards. So I'm going to copy. That needs to be a 4 times, I need another fraction, 4 out of 50. Ooh. See, it wouldn't even give me the fractions. So if I needed this answer in fractions, I would have to actually go 4 times 4 times 4 is 64. So the calculator didn't help me much there. 52 times 51 times 50. Whoops. Is 132,600. So be careful, sometimes the calculator may not help you. Okay, another one without replacement. What is the probability of drawing 2 spades and then a heart? So we haven't done any that we're talking about the sets or the suits, but we can do it. So this is the probability of a spade, and then a spade, and a heart. Well, there were 13 cards in each suit, so 13 spades out of 52. And then the next time, it's going to be 12 out of 51. And how many hearts are there? Well, there's still 13 of them, but there's only 50 cards left in the deck. And then I'm going to multiply those all together. And that is how we do the multiplication rule.